Okay, so we've got a couple of problems here about passive RC filters. We've got a low pass filter problem here, and we've got a high pass filter problem right there. So let's draw a low pass RC filter. So here's our input source. That's what we're feeding the filter with. And we've got a resistor right here, and we've got a capacitor right here. It's a low pass filter. And so at very low frequencies, when this is set to low frequencies, this is going to appear as a lot of resistance. So the reactance across this capacitor is going to be very high when the frequency is very low. And then as the frequency of this increases, the reactance of the capacitor decreases, and eventually all of the voltage from this source is going to be across this instead of that right there. And so that roll-off effect happens as you increase this frequency right here. So let's look at the Bode plot of this low-pass filter. So it looks like this. So this right here is attenuation in dB. And this axis right here is frequency. So this right here is 0 dB. You can see that at some frequency, which is right here, that is the critical frequency, then this filter is going to start rolling off the highs at a slope of minus 20 dB per decade or minus 6 dB per octave. So this is basically a graph of all of the solutions for the voltage across this capacitor here, based on what this frequency could be set to. So let's see this question. It's saying the output of a first-order low-pass filter measures 30 volts AC. So that means we're seeing 30 volts right here. If the signal at the output has been attenuated by minus 15 dB, so that means that's like down here or something. What must the input signal be in volts? Okay, so we know this. There's a formula for attenuation, which is 20 log base 10 V out over Vn, otherwise known as gain. This is gain. And that equals the attenuation in dB. All right. Well, let's look and see what stuff we don't know. We're asked, what is Vn? What must the input signal be in volts? All right, so that's this. So 20 log base 10. Do we know V out? Yeah, they said it's 30 volts. Vn, we do not know. And what is the attenuation in dB at this frequency? It's minus 15 dB. Okay, let's do some algebra. So divide both sides by 20. That goes away. 20 goes over here. Oops. So minus 15 divided by 20 is minus 0.75. Okay, and so we've got log base 10 of 30 volts over Vn right here, and that all equals minus 0.75. Well, how do you make a log base 10 go away? You say all of this to the 10 to the power of all of this, and then you say 10 to the power of all of this. So what happens is the log base 10 goes away, and we're left with 30 volts over Vn. And then over here, we've got 10 to the power of minus 0.75. Okay, Well, we're after Vn here. So 30 divided by 10 to the minus 0.75 equals Vn, which equals what? Well, let's see. 30 divided by parentheses 10 to the minus 0.75. All right. So Vn is going to be 168.7 volts. So 168.7 volts AC. That's the input to this filter. Okay. Well, that solves that one. Let's see what the next one says. This one's asking, a high-pass filter has a critical frequency of 0.80 or of 85 kilohertz. I'm sorry. What frequency would 50 volts AC input source need to be set to in order for Vout to be attenuated by minus 26 dB? And then it asks, what will Vout measure in volts at this frequency? Well, let's draw the filter first. So here's Vn. That's this AC voltage. Here is our high-pass filter. And we're taking Vout across this right here. All right. So the input source is 50 volts. And we're not given the frequency, but they want to know what frequency should this source be set to in order for Vout to be attenuated by minus 26 dB. Okay, well, let's look at the graph of this filter, see if we can figure out this problem. Always good to draw a graph or some illustration. So here's a high-pass filter right here. We know that at this spot, which is the critical frequency or the corner frequency, that's given to us. They're saying that the corner frequency is 85 kilohertz. All right. And we also know that at the corner frequency, the attenuation is minus 3 dB in a first order filter. All right. And then they say there's a frequency, F, that would result in an attenuation of minus 26 dB right there. And they want to know, what will Vout measure in volts at this frequency? All right. Well, first off, I would like to know, what is that frequency that is going to result in this attenuation here? Well, the slope of this line right here is 20 dB per decade. And what is the distance between this frequency and this frequency? It looks to be 23 dB. So delta dB is equal to 23 dB. That's the distance between here and here. And we know this frequency. All right. So delta dB divided by the slope of the line, which is 20 dB per decade. So divided by 20 dB per decade, and the decade comes up here. And so that gives us some number of decades. So 23 divided by 20 is 1.15 decades. Okay. So this frequency right here is going to be 1.15 decades lower than this frequency. So I'll call this F1. So frequency 1 is equal to the starting point, which is 85 kilohertz, times, we're in decades, so it's going to be times 10. And am I going up or am I going down? I'm going down. So I'm going to make this a minus 1.15 decades. Let's see what frequency 1 is. 85 kilohertz times 10 to the minus 1.15, and that equals 6.01 kilohertz. So this frequency here, 6.01 kilohertz. And we have found what that frequency is. And then they ask, what will V out measure in volts at this frequency? Well, what's the attenuation at that frequency? It's minus 26 dB. What's V in? It's 50. So it's just going to be 20 log base 10. V out, that's the thing I don't know, over V in, which is 50. And what is the attenuation at the frequency in question? It's minus 26 dB right there. So let's do some algebra. So divided by 20, divided by 20 right here. So 26 divided by 20 is what? Minus 1.3. And that means we're left with, if my pen would write, we're left with log base 10 V out over 50 equals minus 1.3. Okay, so we're going to say 10 to the power of all this equals 10 to the power of all this. The log base 10 is going to go away. So we're going to end up with V out over 50 volts equals 10 to the minus 1.3. And the 50 is going to swing up here times 50. 50 will go away right there. And let's see. We've got 10 to the minus 1.3 times 50 volts equals 2.5 volts. So that is what V out of this filter is going to be when this frequency here is set to 6.01 kilohertz. So we've done it. All right, that's it for this one.